A rocket returning from space has to do something that sounds almost impossible: land upright without hovering in place. For most vehicles, hovering is a comfort zone. A helicopter can pause. A lunar lander can balance thrust against gravity, but a Falcon 9 booster is different. By the time it comes home, the stage is mostly empty. That makes it much lighter than it was at launch. Even one of its engines at its lowest practical power can produce more thrust than the returning booster needs to simply hang in the air. So if it tried to hover, it would not sit calmly above the landing pad. It would start climbing again. That turns landing into a timing problem. Instead of floating down slowly, the booster follows a controlled fall. It uses the atmosphere, steering surfaces and engine burns to reduce speed. Then, near the end, it performs a carefully timed landing burn. The goal is not to stop high above the ground. The goal is to reach almost zero downward speed at the same moment the legs meet the landing surface. This is why the landing can look so sudden. The rocket is not casually parking itself. It is spending the last of its energy in a narrow window with very little room for waste. What is known is the basic engineering idea: save fuel by avoiding a long hover and use guidance to arrive at the surface at the right speed. What remains difficult is everything the rocket has to handle on the way down: winds changing weight engine behavior and the motion of a drone ship at sea. The fascinating part is that this is not brute force, it is precision. A returning booster is not defying gravity. It is bargaining with gravity until the final second. And that is where the deeper story begins, not with hovering, but with control. The landing begins long before the rocket is close to the ground. A returning booster is falling back through layers of air that keep changing around it. High above Earth, there is almost no atmosphere to push against. Lower down, the air grows thick enough to steer with. So the rocket uses different tools at different moments. First, small control systems help point the stage in space. Then engine burns adjust its path and slow it down. As the atmosphere becomes useful, grid fins near the top of the booster act like metal wings. They do not hold the rocket up like an airplane wing. Instead, they help guide the falling cylinder, nudging it left-right and into the correct orientation. The trick is that the rocket is unstable in a very ordinary way. It is tall, narrow, and moving tail first toward Earth. Without constant correction, small errors can grow. Guidance software watches the situation and commands the hardware to respond. The booster must manage direction, speed, tilt, wind, fuel remaining, and the location of the landing target. At sea, that target may be a drone ship moving gently with the ocean. The final landing burn is the most dramatic moment, but it only works because the earlier descent has already shaped the path. If the booster arrives too fast, too sideways, or too tilted, the final burn cannot magically fix everything. This is known from the way reusable boosters are designed and operated. Descent is a chain of corrections, not a single last-second miracle. But there are still uncertainties in every real flight. Weather can shift. The booster may experience conditions that are slightly different from prediction. The control system has to keep adapting. That is what makes the landing so fascinating. It is a machine making a calm decision inside a violent environment. Not hovering, not falling helplessly. Guided, falling slowed at the exact end. And once that became reliable, the economics of rockets began to change. The reason this landing matters is simple rockets used to be treated like machines you threw away. A first stage does much of the hardest work. It holds engines, tanks, plumbing, computers, and structure strong enough to survive launch. For decades after that, work was finished. Most boosters fell into the ocean or burned up. SpaceX changed the expectation by showing that an orbital class booster could return and fly again. The landing without hovering is part of that change because fuel is precious. Every extra second of engine burn during descent is propellant that could not be used earlier for the mission or must be carried as extra mass. A long hover would be elegant but costly. A short-timed landing burn is less forgiving but more efficient. Reusability is not just about catching a rocket. It is about making the rocket worth using again. After landing, engineers inspect the booster, understand what it experienced, and prepare it for another flight. When it meets requirements, that creates a feedback loop. Each recovered stage becomes both hardware and evidence. What is known is that reusable Falcon 9 boosters have flown repeatedly, and that this has changed expectations for launch operations. What should be stated carefully is the bigger economic picture. Launch cost depends on many things: refurbishment, production, payload needs, scheduling, insurance, and the mission itself. Reuse helps, but it is not magic. The deeper importance is cultural as well as technical. A landing booster tells engineers that a launch vehicle does not have to be a single-use event. It can be closer to an aircraft in spirit, even if rockets remain far more extreme. That is why the no-hover landing is so memorable. It looks like a stunt, but it is really a strategy. Use just enough fuel, arrive with just enough speed, save the machine, and in that final second, spaceflight becomes a little less disposable.